Yes. Hello friends. Welcome to the session. That is continuation of chapter 4, that is inverters. In the last sessions I discussed about in detail about single phase bridge inverters, that is voltage source inverters. Single phase voltage source bridge inverters. Yes. Then I solved so many models also. In classroom workbook I solved so many models based on that concept. In bridge inverters, in details that I given, what is half bridge inverter, what is full bridge inverter, all these concepts I discussed. Okay. Now we'll start with the three-phase bridge inverters. In this session, we will continue with the three-phase bridge inverters. Here again, three-phase voltage source bridge inverters only. The point to remember, here I am telling that three-phase bridge inverter means it's a voltage source inverter. If it is mentioned that current source inverter, then only you can take current source inverter. Understood? Here I am taking three-phase voltage source bridge inverter. Yes, we'll start. All of you concentrate. Start with the three-phase bridge inverters. This is three-phase voltage source bridge inverter. Okay, this three-phase bridge inverters. Three-phase bridge inverters. This is voltage source inverter, three-phase bridge, that is three-phase voltage source bridge inverter. Here I am talking about voltage source inverter now. The only difference between voltage source inverter and current source inverter is if the input is voltage source, that is voltage source inverter. If the input is current source, then that is the current source inverter. Okay, that you know. Yes. The point to remember, this three-phase bridge inverter, it is also called six-step inverter. It is also called six-step inverter. Yes, it is also called a six-step inverter. It is also called six-step because in one cycle we can get six steps. Let us give the proof also. It is also called six-step inverter. Yes, it is operated in two modes. The three-phase bridge inverter circuit is operated in two modes. It is operated in two modes. Okay, it is operated in two modes. It is operated in two modes. Yes, one is 180-degree mode of operation. 180-degree mode of operation. Another one is 120-degree mode of operation. To get the by operating that three-phase bridge inverter in 180-degree mode and 120-degree mode, we can get different wave shapes at the output side. To operate in 180-degree mode and 120-degree mode, then we can get different wave shapes at the output side. That we will see. What are the different wave shapes we are getting at output side operating in 180-degree mode and 120-degree mode? Now, what exactly 180-degree mode? What exactly 120-degree mode also? That I will explain. Okay. First, we will draw what is the three-phase bridge inverter circuit. Okay. Yes, this is three-phase bridge voltage source inverter. That means input is voltage source. Take input is voltage source. Don't wait, parallelly draw the circuit, all of you. Parallelly, all of you draw the circuit. Yes, input is voltage source. Here I am using switch arrangements. Here switch is any semiconductor device you take. I told already what type of devices are used for in voltage source inverter. Which devices are preferable for volt? That devices we can connect. Parallelly, all of you draw the circuit. Yes. In general, we are using bridge inverter means it is a voltage source inverter. It also consists of feedback diodes. Voltage source inverter means it also consists of feedback diodes. 1 minute please. Okay. It also consists of feedback diodes. I am representing with feedback diodes. I am representing with feedback diodes. This is one phase. This is another phase. S. S. This S1 standard notation I am following. S1, S3, S5, D1, D3, D5, S4, S6, S2, D4, D6, D2. Here at input side, we are connecting one capacitor. The purpose of using capacitor is to maintain constant DC at input side. Okay. Then let us assume that this is A phase, this is B phase, this is C phase. Okay. Assume that it is a star connected load. You can also connect delta connected also, but here I am assuming that it is a star connected load. It is a star connected load. With the assumption of star connection, I am explaining this concept. It is a star connected load. S, A phase, B phase, then this is C phase. Then A, B, C, this is neutral point. Okay. This Vs is the supply voltage. Take Vs, or you also take VDC. Take either Vs or VD, any notation you follow. Either Vs you take or VDC you take. Any notation, it may be given. The purpose of using C is to maintain constant DC at input. Constant DC at input. To maintain constant DC at input. So, okay, to maintain constant DC at input. Then it consists of operated in two modes now. This I told already. It is 180-degree mode and this is 120-degree mode. Operated in two modes, 180-degree mode and 120-degree mode. Okay. Now it consists of 6 switches, 6 diodes. Where the diodes are, which diodes? This one, feedback diodes. It consists of 6 switches and 6 diodes. Yes. Hence, it is combination of 3 half-bridge inverters. It is combination of 3 half-bridge inverters. 3 half. Each phase consists of 1 half-bridge. This is 1 half-bridge configuration, and this also 1 half-bridge configuration. This also 1 half-bridge configuration. That's why it is a combination of 3 half-bridge inverters. 3 half-bridge inverters. Yes, listen please. This about some introduction about 3-phase bridge inverters. But now I want to explain this concept in 180-degree mode and 120-degree mode. To explain this concept in 180-degree mode and 120-degree mode, for simplicity, I will assume that resistive loads. Yes, I'm explaining this concept according to our analysis, mainly concentrate on, assume that load is resistive loads. With that assumption, I'm explaining. Understood? Tell me. It is a voltage source inverter. Now, we want to explain this voltage source inverter for resistive load. Okay. It's completed. Over. Quick. Note down. This D1, D3, D5, D4, D6, D2 are the feedback diodes. S1, S3, S5, S4, S6, S2 are the main switches. S1, S3, S4, that is S5, S6, all these are that is S1, S2, S3, S1, S2, S3 are the main switches. These are main switches. We know that the devices which having bidirectional capability, those devices are used in the voltage source inverter. One of the example is, the switch may be like this. A BJT with anti-parallel diode. This is used. A thyristor with anti-parallel diode, that is a thyristor with feedback diodes also we can use. The point to remember, the switch which having the bidirectional capability, those switches are used in the voltage source inverter. That I already given even in discussion of differences between VSI and PSI. Yes, the devices which having the bidirectional capability. This is one of the example. What type of switch we are using here? Understood. The another point to remember here, VAN, VBN, VCN are called phase voltages. These are taken as a phase voltages. VAN, VBN, VCN is taken as a phase voltages. Then another point to remember, VAB, VBC and VCA. VAB is written as VAN minus VBN. VBC is written as VBN minus VCN. VBN minus VCN. VCA is written as VCN minus VAN. Then these are taken as a line voltages. These are taken as line voltages. Let if you assume that this is total supply voltage Vs na, the total supply voltage is Vs means total supply voltage is Vs means, then this voltage can also be represented like this. Let this is Vs by 2 and this is Vs by 2. If we represent like this Vs by 2 and Vs by 2, then this point is taken as a, if we represent like this Vs by 2 and Vs by 2, the sum of the voltage total gives the Vs. Then this is grounding point. If you assume that this is the grounding point, then from A phase to this grounding point VA0, from B phase to this grounding point VB0, then what these voltages are called? VA0, VB0 and VC0. These are called pole voltage. Pole voltages in the sense switch voltage. This is called pole voltages. Okay, this point VA0, this VB0, this VC0, that voltages are measured as a pole voltages. In any 180-degree mode or 120-degree mode, like this only you can consider. These are taken as a phase voltages, and these are calculated as a line voltages, and these are considered as a pole voltages. Understood? Okay. Now, first we will start with the 180-degree mode for R load. In this concept, I want to discuss during the operation of this inverter circuit in 180-degree mode, if different pair of devices are conducting, what is the phase voltage and what is the line voltage that I want to calculate. After calculating phase voltage and line voltages, then we want to draw the waveforms. Then we can prove that we are converting DC to three-phase AC. Then after drawing the waveforms, we can analyze what is the shape of the phase voltages, what is the shape of the line voltages. Once you know the shape of the phase voltage and line voltages, then we can use the general analysis. That I want to discuss here. Understood? Now, first we will start with the 180-degree mode. Yeah, it's okay. First we will start with the 180-degree mode. A three-phase bridge inverter in 180-degree mode. That I want to discuss. Listen please. Concentrate on 180-degree mode for R load. This I am explaining for R load, 180-degree mode. A three-phase bridge inverter in 180-degree mode. Concentrate on R load. We know this concept. It is a voltage source inverter, that's why we are using feedback diodes. For R load, no need of feedback diodes. For resistive load, no need of feedback diodes. No need of feedback diodes. That concept you know. That I already explained. No need of feedback diodes. Then remove this feedback diodes. Redraw the circuit. All of you once again redraw the circuit. Remove this feedback diodes. And replace load by resistive load. All of you redraw the circuit without feedback diodes. Because this concept I am explaining for resistive load. Yes? Listen please. And in this analysis, no need to consider all this capacitor arrangement, all this. Let the supply voltage is Vs or VDC. You take supply voltage Vs or VDC. This is S1. S1, S3, S5. This is A phase, B phase, C phase, S4, S6, S2. Don't have any diode. Then replace the load by resistive load. R load. This also replace with R load, and you also replace with resistive load. Let us assume that it is a star connected load. This is neutral point. Yes. Tell me. This is a circuit we are using for resistive load using 180-degree mode. Now tell me. What do you mean by 180-degree mode means? In 180-degree mode, the conduction of devices are allowed like this. If the conduction of devices are allowed like this, then it is called 180-degree mode of operation. The conduction of devices is 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, yes, 5, 6, 1, 6, 1, 2. In one cycle, if the conduction of devices is allowed like this, then it is called 180-degree mode of operation. Except, this is one cycle because this total is one cycle. Here we are drawing the waveforms for one cycle only, 360 degrees. 360 degrees. This is 60 degrees. This is 60 degrees. This is 60 degrees. And this also 60 degrees. And this one is 60 degrees. And this is also 60 degrees. Yes. 60, 120, 180, 240, 300, 360. Each device is allowed for 180 degrees. That's why it is called 180-degree mode. How it is? Each device is allowed for 180 degrees. Yes. Concentrate please, all of you. Here, for example, let us assume that already 612 is conducting. Before this already 612 is conducting means here 6 is turned on, 3 is on. Assume that here we have triggered the switch 3. Then it is conducting how much angle? Here 3 is conducting, here 3 is conducting, here also 3 is conducting. How many degrees is it conducting? 60 plus 60 plus 60, 180 degrees. Now here 1 is turned off, 4 is triggered. At this instant 4 is triggered means how much angle 4 is conducting? This is 4, here 4 is conducting, here also 4 is conducting, here also 4 is conducting. 60 plus 60 plus 60, how many degrees? 180 degrees. Then here 5 is triggered. Here 5 is triggered means how much angle? 5 is conducting, 60, 60, 60. Each device is allowed to conduct for angle of 180 degrees. That's why it is called 180-degree mode of operation. But point to remember, each switch is triggered at angle of 60 degrees. Each device is, each switch is allowed to conduct for angle of 180 degrees, no doubt at all. But at every 60 degrees we are triggering the switch. Here switch means it may be BJT, or it may be MOSFET, or it may be thyristor, like that, or it may be IGBT, any switch. That is the meaning. Okay. That means every switch is, here third is triggered, here fourth one is triggered, here fifth, switch 5 is triggered, here switch 6 is, here switch 1 is triggered, here switch 2 is triggered. At every 60 degree instant we are triggering the switch. But each switch is conducting how much angle? 180 degrees. That's why it is called 180-degree mode of operation. Now, in this, different devices are conducting. If 1, 2, 3 is conducting, 2, 3, 4 is conducting, 3, 4, 5 is conducting, 4, 5, 6 is conducting. If the different devices are conducting, I want to calculate what is the phase voltage, what is the line voltage. Once you know the instantaneous phase voltage and line voltage, then we can draw the waveforms. Understood? Okay. Here, I am not drawing the waveforms from the starting. Let us assume that already operation is started. Already some devices are conducting. Already 1, 2, 3 is conducted. 2, 3, 4 is over. 3, 4, 5 is over. 4, 5, 6 is over. Like that. Already some devices are conducting. After conducting all these devices, let us assume that 561 is conducting. 561 is conducting. 561 is conducting. If 561 is conducting, now I want to calculate what is instantaneous phase voltage and what is instantaneous line voltage. Once you know the instantaneous phase voltage, calculation of line voltage are very easy. But again, no need to calculate every time what is the line voltage. Once you know the phase voltage means, for example, I know the VAN and VBN. Then what is the VAB? VAN minus VBN. This is a vector difference. Understood? Now 561 is conducting means now I want to calculate what is the A phase, what is the B phase, what is the C phase voltage. I'm not started at 1, 2, 3 because I want to draw the waveforms after some cycles. Understood? Let's assume that now the 561 is conducting. From this 561 is conducting, what is the equivalent circuit you tell me? If 561 is conducting, that this is the supply voltage Vs. Vs is the supply voltage. Vs is the supply voltage. This Vs. One is on state. One is on state. S1 is on state. This S4 is off state. S4 is off state. 3 is off state. You are not triggered S3. S6 is on state. 5 is on state. S5. But 2 is off state. We are not triggered 2. Yes, this is A phase. This is B phase. This is C phase. I am drawing the equivalent circuit if 561 is conducting. Okay. I am drawing the equivalent circuit if 561 is conducting. All of you follow parallelly. All of you draw this circuit. Don't wait. This is R. This is R. This is R. This is neutral point. A phase, B phase, C phase. 1 is on state. 561. 5 is on state. 6 is on state. Remaining are off state. With this, I am drawing this equivalent circuit from this one. S4 is off state. Now remove this. S3 is off state. Now remove this. S2 is off state. Now remove this. This is the equivalent. Okay. Now, once again you simplify this one. What you get? You tell me. Once again you simplify this. What you can get? Listen, please. This A phase is connected to positive plate. C phase is connected to negative. Sorry. C phase is also connected to positive plate. Then what about B phase? This B phase is connected to negative plate. You redraw the circuit. Then what you get? This is Vs. Clear? A phase is connected to positive plate. This is A phase. A phase is connected to positive plate. And B phase is connected to positive plate. Then, sorry, C phase is connected to positive plate. This is R and this is R. This is the neutral point. This B phase is connected to positive plate. Sorry, this is B phase. Let the current is I. Then how to define I equal to? Vs by R by 2 plus R. That equal to 2 Vs by 3R. S. I equal to Vs by R by 2 plus R. That equal to 2 Vs by 3R. Clear? Then, now I want to calculate A phase voltage and C phase voltage. This A phase and C phase is in parallel. Na? A phase and C phase is in parallel. Then you define what is VAN and VCN. Okay. Can you define like this? Tell. Yes. Can you define like this? VAN equal to VCN equal to S, both are parallel. VAN equal to, this is neutral point, VCN equal to I into R by 2. What is I? You know, that is 2 Vs by 3R. That you substitute. What you can get? Vs by 3. Yes. Now, can you define? Mainly current is enter at this point now. Current is enter at this node means we can define VNB. Then what is VNB? VNB equal to I into R. That equal to 2 Vs by 3. But I want VBN. VBN equal to minus 2 Vs by 3. These are the phase voltages. If 561 is conducting, these are the phase voltages. This is, if 561 is conducting, these are the phase voltages. Understood? But every time drawing the equivalent circuit, calculating phase voltages, line voltages is lengthy process. Once you know the phase voltages, then how to calculate line voltage here? If you calculate line voltage means that you know VAB equal to VAN minus VBN. I don't want to simplify, just I am writing. VBC equal to VBN minus VCN. Okay. VCA equal to VCN minus VAN. It's okay. Now, if 561 is conducting, similarly, 612 is conducting. What is A phase? What is B phase? What is C phase? That I want to calculate. Similarly, 1, 2, 3, 2, 3, 4, 3, 4, 5, like this. Different devices, different pair of different devices are conducting. What the phase and the line voltages we want to calculate. But every time doing this analysis, calculating this is lengthy procedure. That's why without doing this analysis also directly you can answer. Without doing the analysis also directly you can answer. Understood? Yeah. Tell me. One observation from this one. To write the formulas directly, one observation. Listen please. If the two phases are connected to same plate, A phase is connected to positive plate. This is A phase now. This is A phase. This is C phase. Okay. A phase is connected to positive plate and C phase is also connected to positive plate. If the two phases are connected to same plate, then voltage is equal to Vs by 3. If only one phase is connected, voltage is 2 by 3 Vs. If it is connected to positive plate, it is positive. If it is connected to negative plate, it is negative. Understood? Now, with this observation, then you write the formulas directly. Yes, you tell me. For this, to write these formulas directly means, then what is the group? We can take this one. This is 1, 3, 5 in bridge. Okay. 1, 3, 5. This is A phase. This is B phase. This is C phase. This is 4. This is 6. 2. Then this is, you take positive group. Then you take this is negative group. Again, no need to draw the figure. Total circuit, no need to draw. Just you take this one like this. Now tell me. Next one is 612 is conducting. Tell me. 612 is conducting. Without doing analysis, directly I want to write A phase, B phase and C phase voltages. Once you know the phase voltage, calculating line voltages are very easy. 612 means, 6 means which phase? 6 means which phase? 6 means B phase. 6 means B phase negative. Because this is negative group. This is positive. 6 negative group B phase. 1 means which phase? A phase positive group. 2 means which phase? 2 means which phase? C phase negative. Now these are connected to same plate na negative plate. B and C is connected to same plate. If B and C is connected to same plate means then both are equal. VBN equal to VCN equal to Vs by that observation I given. If the two phases are connected to same plate, voltage is Vs by 3. But it is connected to negative plate. Negative plate na, that's why you take minus. Then what is VAN? VAN equal to 2 by 3 Vs. And this is if 612 is conducting. 612 is conducting. Now similarly you tell me, if 123 is conducting. First I want to list out all the phase voltages, later on we draw the waveforms. Every time no need to do the analysis, directly you are answering. All these are the instantaneous phase voltages. Once you know the phase voltage, calculating line voltage are easy. Now tell me, if 123 is conducting. 123 is conducting means 123 is conducting means 1 means which phase? 1 means which phase? A phase positive. 2 means which phase? C phase negative. 3 means which phase? B phase positive. That you know. From this I am writing. Okay. Now this A phase and B phase is connected to same plate now. If A phase and B phase is connected to same plate means VAN equal to VBN equal to Vs by 3. Now what is VCN equal to? Minus 2 by 3 Vs. If only one plate is connected, 2 by 3 Vs. If it is connected to negative plate, minus. If it is connected to positive plate, plus. Okay. Next, 1, 2, 3. Next one is 2, 3, 4 is conducting. 2, 3, 4 is conducting. Tell me. 2 means which phase? C phase negative. 3 means which phase? B phase positive. 4 means which phase? A phase negative. Okay. Then tell me. C phase, these two are connected to same plate now. Once these two are connected to same plate means VAN equal to VCN equal to minus Vs by 3. Then VBN equal to 2 by 3 Vs. 2, 3, 4 is conducting. Similarly, now you tell me 3, 4, 5 is conducting. 3, 4, 5. If 3, 4, 5 is conducting means 3 means which phase? B phase positive. 4 means which phase? A phase negative. 5 means which phase? C phase positive. Then these two are connected to same plate. If these two are connected to same plate means, now you tell me, VBN equal to VCN equal to Vs by 3. Then what is VAN? VAN equal to minus 2 by 3 Vs. Can you try for 4, 5, 6 is conducting? If 4, 5, 6 is conducting, 4 means which phase? 4 means A phase negative. 5 means which phase? C phase positive. 6 means which phase? Then B phase negative. These two are connected to same plate. VAN equal to VBN equal to minus Vs by 3. Then what is VCN equal to? 2 by 3 Vs. Okay. Like this, different phase voltages we are representing. 5, 6, 1, 6, 1, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6, again 5, 6, 1. Again cycle will be repeated. But we are drawing the waveforms only for one cycle. Understood. Now we will draw the waveforms. By knowing this one, now we will draw the waveforms. Now see. Here I am drawing 3 phase voltage waveforms and 1 line voltage waveform. You also draw the 3 line voltage waveforms also. For simplicity, I am drawing 3 phase voltage waveforms and 1 line voltage waveform. That you concentrate. Yes, all of you concentrate. Parallelly, all of you draw the waveforms. this omega t axis. Yes. Concentrate on three phase voltages, waveforms, one line voltage waveform I am drawing. This is VAN, this is VBN, and this one is VCN, and this is VAB. S can represent with is 2 by 3 Vs, that is Vs by 3, minus 2 by 3 Vs, sorry, this is minus Vs by 3, minus 2 by 3 Vs. This is B phase voltage, no? Yes, this is B phase voltage, VBN. Okay. Then this is Vs 2 by 3 Vs, this is Vs by 3, minus Vs by 3, minus 2 by 3 Vs. This is 2 by 3 Vs, Vs by 3, minus Vs by 3, minus 2 by 3 Vs. Later on we will draw the line voltage also. Here I am drawing three phase voltages and one line voltage waveform. Okay. And this is 561 is conducting. This is 612 is conducting. 561, 612 is conducting. This is 123 is conducting. This is 234 is conducting. 1, 2, 3, 4, 5, 6. This is 561, 612, 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 6. Like this it is conducting. Now tell me. First I am drawing A phase, next B phase, next C phase. Once you know the A phase, B phase, C phase, then we can draw the line voltage waveform. Okay? You tell me. If 561 is conducting, 561 is conducting, what is the A phase voltage? A phase voltage equal to Vs by 3. This is A phase voltage is Vs by 3. Next, 612 is conducting. What is the A phase voltage? Minus Vs. 612 is conducting. What is the A phase voltage? 2 by 3 Vs. 2 by 3 Vs. 123 is conducting. What is the A phase voltage? Vs by 3. Next, 123 is conducting. A phase voltage is Vs by 3. Like this, we can take all these values. Then directly I am drawing. Then we can get 2, 3, 4 is conducting. Minus Vs by 3. 3, 4, 5 is conducting. Minus 2 by 3 Vs. 4, 5, 6 is conducting. 4, 5, 6 is conducting. Minus Vs by 3. Can get this like this. Okay. This is one cycle. 60, 120, 180, 240, 300, 360. This is one cycle. 4, 5, 6 is conducted. Okay. Now, we want to draw the B phase voltage. Then if you draw the B phase voltage wave shape means, B phase voltage means, 561 is conducting. What is the B phase voltage? Minus 2 by 3 Vs. Minus 2 by 3 Vs. 612 is conducting. What is the B phase voltage? Minus Vs by 3. Like this, you take all these values. 1, 2, 3, 2, 3, 4, 4, 5, 3, 4, 5, 4, 5, 6. All these you take. Then you represent here. Then y can. Next, minus Vs by 3. Minus 2 by 3 Vs. Next, plus. This we can get minus Vs by 3. Plus Vs by 3. 2 by 3 Vs. Plus Vs by 3. Plus Vs by 3. Then we can get minus Vs by 3. Okay. This about B phase. Then similarly you draw the C phase voltage wave shape. C phase voltage means if 561 is conducting, what is the C phase voltage? C phase voltage is Vs by 3. Then 612 is conducting. If 612 is conducting, what is the C phase voltage? Minus Vs by 3. Like this you represent. Then we can get minus 2 by 3 Vs. Minus 2 by 3 Vs. Then minus Vs by 3. Then plus Vs by 3. Next 2 by 3 Vs. Okay. These are the phase voltage waveform. A phase, B phase and C phase voltage wave shape. Okay. Now can you draw the line voltage waveform? Here I am drawing only one line voltage waveform. You also draw VAB. You also draw VBC, VCA also. For simplicity, I am drawing only one line voltage. For analysis purpose, this is enough. Okay. Then remaining shapes are same. Just it will be shifted only. Some angle it will be shifted. Understood? Can you draw the VAB? VAB means how to draw the VAB? How to draw the VAB means VAB is nothing but VAN minus VBN. VAN minus VBN. We represent with VAN minus VBN. You calculate VAN minus VBN. VAN minus VBN, that you do at every instant. What is VAN? You tell me. VAN equal to, if 561 is conducting, what is VAN? 2 by 3 Vs minus, what is VBN? You tell me. Minus 2 by 3 Vs. This minus into minus plus, then how much you can get? This one. VAN is Vs by 3. Vs by 3 minus of minus 2 by 3 Vs. Then we can get Vs. Okay. Then you can represent VAB equal to Vs. What I am doing? VAN, VBN is subtracting. Then similarly you do. This one is 2 by 3 Vs. Minus of minus Vs by 3. You can get Vs. Just I am subtracting. 2 by 3 Vs. Minus of minus Vs by 3 Vs. Next, Vs by 3 minus Vs by 3 minus Vs by 3, 0. Okay, next, minus Vs by 3 minus of minus Vs by 3 minus, this is plus 2, then we can get minus Vs. Just we are subtracting. Again minus Vs. Then again 0. Okay. This we are getting. This is line voltage waveform. Yes, this is one line voltage waveform, and this is C phase voltage, this is B phase voltage, and this is A phase voltage. Understood? Okay. How this, by using three-phase bridge inverter in 180-degree mode, how we are converting this DC voltage into three-phase AC. This is one-phase voltage waveform. This is one-phase voltage waveform. This actually it is not a pure sinusoidal, but the fundamental component may be sinusoidal. It is not a pure sinusoidal. The fundamental component may be sinusoidal. If you take only fundamental component, the fundamental component is sinusoidal. Okay. If you take only fundamental means then what you can get? The fundamental component may be sinusoidal. This one waveform. Yes, you take this also. This also one waveform. You take this is also. You consider. Like this we are getting three-phase voltage waveforms. This is A phase, this is B phase, this is C phase. Then each phase is shifted by 120 degree. The phase difference between the phase voltage must be 120. That is satisfied here. Yes or no? This is 0 degree. Assume that it is 0 degrees. Then 60 plus 60. After 120 degrees it is started. Then after 240 degrees it is started. The phase difference between A phase and B phase is 120 degrees. The phase difference between B phase and C phase is 120 degrees. This is 0. This is 60 plus 60, 120. This is 60 plus 60, 120. The phase difference between each phase is 120 degrees. Understood? Okay. Like this, we are converting a DC voltage into three-phase AC by using 180-degree mode of operation using three-phase bridge inverter. Understood? Now, based on these waveforms, we want to list out some points. Those points are important for any competitive point of view. Based on this, we want to list out some points. Those points are important for any competitive point of view. That you will see. Then, what is the shape of the phase voltage? What is the shape of the line voltage? What is the amplitude of line voltage? What is the amplitude of phase voltage? All these points I want to discuss. After summarizing those points, then you go for analysis of phase and line voltage. Clear? Understand? Note on this. What is the amplitude of this? What is the amplitude of line voltage? You tell me. The amplitude of line voltage is, this is Vs and this is minus Vs. This how we are getting that, you know. VAN minus VBN, VAN minus VBN, VAN minus VBN. That I am doing. This is plus Vs and this we are getting maximum amplitude, plus Vs and minus Vs. First concentrate this, note down this waveform. In the next session we will continue with what is the analysis of these waveforms and what is the point important with respect to 180-degree mode. Then you go for the 120-degree mode of operation. Understand? Clear? Okay. Thank you.